Chapter 17, Part 3, Diffraction Gratings and Multiple Slits. So now we're going to get into diffraction gratings. So this is where before we were dealing with two individual slits and we were shining light through them. So now we're going to see what happens when instead of two slits, we get a whole bunch more. So when you get multiple slits, the whole idea of that, so the benefit of it, is that we want to isolate these bright bands. So if you look at this one right here, you can find that there are definitely clear areas of constructive interference. But we want to narrow it down to find exactly where the center of it is. So when you have two slits, you get these wide bands. When you've got more slits, you get much more narrow bands, like this. So it widens the dark and enhances the bright bands. To get the number of slits, it's usually given from something called n. So from this value n. So n is the number of slits. So the number of slits divided by the length. Or number of slits over d. So let's say that we have n equals 1,000 slits per centimeter. What is the distance between the slits? We can remember that each of the slits is approximated to be about the same size, about 1/10 of a millimeter, I believe that was. So the slits are all approximately the same size. So that's not what we're asking how wide they are, we're asking how far they are apart. So to do that, we have that n equals 1,000, 1 over a centimeter. So that's 1,000 slits in 1 centimeter. We want to get that into meters. So that is equal to 10 to the 5 slits in 1 meter. D, so the distance between the slits, is 1 over n, because we want to find just the distance between one set of slits. So that equals 1 over 10 to the 5, 1 over 10 to the 5 inverse meters. 1 over 10 to the 5 inverse meters, which will then say that each of these slits has a spacing of 10 to the minus 5 meters. So there is one slit for every 10 to the minus 5 meters. That's what that's saying. As n increases, so as this n, as that goes up, the width of the bright bands decreases. However, the number of maxima will stay the same. So even though each of these slits is more defined as we get more slits, even though these fringes are more well defined, you'll see that we still have the same number in each. So in this we have n equals 2. We have these very bright fringes. Once we get to an n equals 10, they're peaking a lot more, so we have isolated spots that are a lot brighter than the dark spots. By the time that we get to 50, we have very clear maxima. So when you're looking at something like this, it can be hard to tell exactly where the brightest part is, where the maxima of any of these individual spots is. The more slits you get, the more you can find out that the maxima is right there. So as the number of slits in the grating increases, the fringes get narrow and bright, more narrow and bright. Spectroscopy. You guys have dealt a lot with spectroscopy, I imagine, in chemistry, or at least I would hope, or at least I hope you know what that word is. This is where we separate out the individual components of light. In an atom, when it gets excited, it gives off characteristic wavelengths. These characteristic wavelengths are able to be separated out. The longer the wavelength that a light gives off, the more it will diffract. The shorter the wavelength, the less it will diffract. You'll see that if you were to look at like a tube of hydrogen gas, what you would see is we have our central maximum. It almost looks white because it's got a whole bunch of colors all reaching the same point. Then as you look around and you look at as you just look like up and down beyond that maxima, you start to see different colors separate. You'll see with hydrogen, I think it's like an orange, a green, and a blue. Those all separate, and you'll see each of those individual colors. They all diffract different amounts based on their wavelength. That means that if you were to have a sample and you excited it and you saw those wavelengths in those positions, you would then know that that sample contained hydrogen or helium or whatever you were looking to see. All elements will always have the same spectra as themselves. If you're able to find those wavelengths and find the spectra of a sample, you can identify what that spectra is composed of. Section 4, thin film interference. When we look at how light travels, when light hits a boundary, it can reflect and transmit. It can reflect as well as transmit at the boundary of different materials. The interesting part about this is that not only can it reflect or transmit, it can do both at the same time. It can both reflect and transmit. So that means that it can both hit the boundary and then go back off of it, or it can hit the boundary and keep going, and it does both of those simultaneously. A wave undergoes a phase change. A wave undergoes a phase change if it reflects from a boundary with a higher index of refraction. This phase change is equivalent to a half wavelength being added to the distance. There are two possibilities since it both reflects and transmits. So since it reflects and transmits, we are dealing with two waves. Two possibilities are neither or both waves have a phase change. If either both waves change or neither wave changes, we get a net path length change of 0. If both waves change by a half wavelength, then they will combine to be one full wavelength, which is the same thing as before. Or if neither changes, then that's pretty straightforward. The other possibility is that only one wave has a phase change. So, for example, it may hit the boundary and then keep going and reflect off of another medium that has a lower index of refraction, so it wouldn't get that second phase change. In this case, the waves have a phase difference of 1/2 wavelengths. If the film is much thinner than the wavelength, now remember the scale that we're talking about here. Most light waves of color are, let's say, around 600 nanometers, like that orange light that we saw on the previous page. If we have a film that is less than, let's go with 600 nanometers, these are the conditions that apply. For a very thin film, we get no phase shift from the extra path length. As the light travels through a medium, since it does technically travel more of a path length, it can pick up a phase change from that. In this case, we're saying that the film is so much thinner than the wavelength that there is no extra path length. The top reflection will also have a 180-degree phase shift. The bottom does not. This would be the same as a half wavelength phase shift. A thin film will give destructive interference for all wavelengths. This causes the film to appear black. So in a thin film, when it becomes black, it is pure destructive interference. I'm going to end part 3 here, and we will pick this back up in part 4.